Dear students, I welcome you all to the third and final presentation on thin and thick cylinders. In this presentation, to begin with, we will be seeing some examples on thin cylinders to begin with, and then we will be just discussing the theory of thick cylinders. Now, let us try to go through the first example that we have here. So, what pressure may be allowed in a cylindrical boiler 2.5 meter internal diameter with plates 20 mm thick if the safe intensity of tensile stress is 65 megapascals. So, if we just try to check the given data, we have the internal diameter which is 2500 millimeter and thickness is 20 mm. The information that has been given here is the allowable stress in the material is 65 megapascals. As you know, in the wall of a thin cylinder, we have two normal stresses, that is the circumferential stress and the longitudinal stress, and the longitudinal stress is always greater than the circumferential stress. Sorry, the circumferential stress is always larger than the longitudinal stress. Hence, we equate the circumferential stress to the given permissible stress or safe stress equal to 65 megapascals. And we know the expression for the circumferential stress, which is given by PD by 2T. So, what we want is to calculate the value of the safe pressure that we want. So, we rearrange this expression, okay, which would be P pressure is less than equal to sigma C into 2 times T by D. So, if you just try to substitute the value, you get the pressure as 1.04 megapascals, and this is the maximum pressure we can allow in the wall of the cylinder if the stress in the cylinder is less than 65 megapascals. I hope you could get this simple example. So, let us try to go through another example that we have here. So, in this particular problem, you have a cylinder of diameter 1500 mm and it is subjected to an internal pressure of 1 megapascals. The cylinder is made of sheets, okay, and as you know, we have got joints both along the longitudinal direction and the circumferential direction, and the efficiency of the joint has been given here, which is said to be 60%, and since he has not specified different efficiencies for circular and longitudinal joints, we assume the efficiencies to be the same for both the joints. Hence, we try to say that the efficiency of the longitudinal joint is equal to the efficiency of the circular joint, which is equal to 0.6. Okay, and we are trying to find what is the thickness, minimum thickness that we have to provide, okay, for the pipe in this particular case. So, the most important relation that we need to understand is you just try to understand a condition, that is, we have to compare the efficiency of the longitudinal joint with respect to 2 times efficiency of the circular joint. So, that is a critical condition that we are trying to talk about. For this particular data, so we can easily understand that the efficiency of the longitudinal joint is less than 2 times the efficiency of the circular joint. So, that means, okay, what you need to understand here is, okay, the longitudinal joint is not very strong when compared to that of the circular joint. If that is the case, then you need to understand that the circumferential stress is the one, okay, that would be critical in this particular case. So, the governing design equation that we are trying to talk about is of the circumferential stress. As you understand, the circumferential stress is given by sigma C equal to PD by 2T, but since you have the joints, you have to have this efficiency factor also coming into the equation. So, we have here sigma C into eta L equal to PD by 2T. So, what you need to understand is when you are trying to talk about the circumferential stress, it acts perpendicular to the longitudinal joint, and hence the efficiency we are trying to talk about is eta L, not eta C. So, in this particular equation, what we want is thickness. So, you can rearrange this particular equation, and one more thing that you need to understand here is we equate the circumferential stress with the maximum permissible stress that has been given here, which happens to be 150 megapascals. So, we rearrange this equation. So, we try to say that T should be greater than or equal to PD by 2 times sigma C into eta L. So, all information is available, substitute, simplify, and the minimum thickness that we have to have in this particular case is 8.33 millimeters. right. So, let us try to go to example 3. In example 3, what we have is again a cylinder, thin cylinder made of joints, but the data that we are trying to talk about in this particular case here are, okay, that is the efficiency of the circular joint and the efficiency of the longeal joint are not the same, unlike the previous case. So, in this particular case, the efficiency of the longeal joint is 0.9 and the efficiency of the circular joint is 0.4. So, we just try to compare the efficiency of the longeal joint with 2 times the efficiency of the circular joint. You are just trying to understand that, okay, the value of eta L is more than 2 times eta C. So, that means what? The longeal joint is more stronger than the circular joint. So, that means, okay, the critical joint would be the circular joint. If the circular joint is the critical joint, the stress acting perpendicular to the circular joint is the longeal stress. So, you need to understand this particular concept. Okay. So, further the data that has been given here is D equal to 1000 millimeters, that is the internal diameter, and the thickness has been given to be 15 millimeter. So, we are trying to calculate the safe or minimum pressure that we can permit in the cylinder. Right. So, coming to the governing design equation. So, you need to understand that because the circumferential joint is more critical. So, we are trying to write the equation for longeal stress. So, longeal stress, as you know, is PD by 4T, but because we have the joints, we bring in the efficiency factor into picture. So, we have got eta L and sigma L into eta C equal to PD by 4T. So, another important thing that we are trying to talk about is we again have to equate the given allowable stress to the longeal stress, which happens to be 50 megapascals. We want to calculate the safe permissible stress. So, if you just try to rearrange that particular equation, so you get the safe minimum pressure as less than equal to, that is sigma L, okay, into 4 times, okay, that is eta C into T divided by D. So, you know all those parameters, substitute and you get the value as 1.2 times megapascal. So, that is the maximum pressure we can have. So, the pressures have to be less than that to keep the stress levels less than 50 megapascals. Now, the last example that I have here is a different one, that is we have a cylinder, okay, whose data is the diameter is 1000 millimeter internal, the length happens to be 3 meters or 3000 mm, thickness is 10 millimeter and the internal pressure it is carrying is 3 megapascals, and the material properties are Young's modulus is 210 GPa and nu the Poisson's ratio 0.3. So, we want to understand, so what are the changes in diameter, changes in length, changes in volume and the maximum shearing stress, that is that the wall of the cylinder is subjected to. So, this is what we are trying to calculate. So, let us try to understand. The first one is the change in diameter, right. As we have derived an expression, okay, for this particular case, the first thing that we need to understand is change in diameter, okay, is linked to what is called as the circumferential strain. Okay. So, circumferential strain and diametral strain are the same. So, we are just trying to calculate the circumferential strain to begin with. So, we have derived this particular equation. So, epsilon C is PD by 4 TE into 2 times 2 minus nu. So, we know all the values of all the parameters on the right hand side. So, we need to be consistent with the units. So, once you calculate this, so we get the value of epsilon C, that is the circumferential strain, as 6.1 in 10 to the power minus 4. So, further we equate the circumferential strain to the diametral strain, which is calculated as delta D by D. So, what we want is delta D. So, we just try to rearrange this particular expression. So, delta D is epsilon C times D, circumferential times the diameter. So, you just try to substitute the numbers. So, you get the change in diameter as 0.61 millimeters. I hope you understood. This is simple. So, first calculate the circumferential strain, then equate it to the diametral strain delta D by D, rearrange, you get delta D as epsilon C into D. Now, similarly, we are trying to talk about the longeal strain. So, longeal strain is calculated as PD by 4 TE into 1 minus 2 nu. This expression is again very similar to the previous expression. You have you know the numerical values of all the parameters on the right hand side of the equality. Substitute, simplify, you get the value of longeal strain. Okay. So, once you know the longeal strain, as you understand, longeal strain is calculated as the ratio of change in length by the initial length, correct. So, I want to calculate the change in length. So, again you rearrange. So, delta L is epsilon L times L. So, substitute the values and you get the value of change in length, which is nothing but 0.4 0.43 millimeters. Now, coming to the next one, that is change in volume is what we are trying to talk about. Okay. So, let us try to understand how we try to calculate this information, right. So, first thing is calculate the internal volume of the cylinder. Please understand, it is the internal volume. So, how do we calculate this particular quantity? It is the area pi by 4 into d square into L. So, that should give you the volume of the cylinder that we have here. So, once you know the volume, we try to calculate the volumetric strain, and we have derived this particular expression in the earlier presentation. So, volumetric strain is equal to 2 times the circumferential strain plus 1 times the longitudinal strain. You have just now calculated the circumferential strain and longitudinal strain. So, we will substitute those values. Once you substitute the values, you get the value of the volumetric strain. In this case, it happens to be 13.63 10 to the power of minus 4. So, once you have got the volumetric strain, so you know by definition volumetric strain is the ratio of delta V by V, that is change in volume by the initial volume. So, we just try to rearrange this expression, you get delta V, that is change in volume. So, delta V equal to epsilon V times V, okay, which happens to be that big number over there. That is how you try to calculate the change in volume. Now, coming to the last part of the problem. So, the last part of the problem is, okay, that is the maximum shearing stress that we are trying to talk about here, right. So, as you understand, we have one more simple expression to calculate the maximum shearing stress, which is nothing but PD by 8T, right. So, you know all the values over here, that is we try to substitute the values over here, and straight away you get the value as 37.5 megapascals, right. So, I hope students, you have understood these 4 examples. Okay, they are quite simple. You need to understand the logic in which we try to do these kind of examples, right. So, with this you need to remember a couple of expressions, that is expressions for circumferential stress, the longitudinal stress, the maximum shearing stress, and the volumetric strain, circumferential strain, the longitudinal strain. I think you should be able to do this, and one more important thing is the efficiency of the joints, right. If we just try to understand these simple concepts, you should be able to do any simple kind of design problems with respect to the thin cylinders. So, let us move on to the next part of the presentation, that is the thick cylinder theory, right. All the while we were talking about thin cylinders. So, to begin with, let us try to understand some basic differences between thin cylinder theory and thick cylinder theory. So, coming to thin cylinder theory, which you already have discussed, right, we have said that the average circumferential stress, okay, is almost equal to the maximum circumferential stress, okay, and hence we try to understand that we try to assume that the variation of the circumferential stress is uniform. That is what we were trying to talk about. But in case of thick cylinder theory, if you just try to calculate the average circumferential stress, okay, over the wall thickness of the cylinder, okay, and then try to compare with the maximum value of the circumferential stress, you will try to understand that, okay, the average stress is much smaller than the maximum stress, okay, and hence, okay, you cannot assume the circumferentials to be uniform. You have to consider the variation of the circumferential stress in this particular case. Now, coming to the radial stress. So, we said that the radial stress is very small and hence is neglected in case of thin cylinder theory. But however, in case of thick cylinders, okay, because the thickness is large, because the pressures are large, we are trying to keep this thickness to be much bigger in case of thick cylinders. So, the radial stress is quite significant, and hence we cannot ignore the radial stresses in this particular case, that is thick cylinders. We try to consider even the radial stresses. Now, in case of thin cylinder theory, we were just talking about a biaxial state of stress. Okay, that is, we had only the circumferential stress which acts along the circumference and the longitudinal stress which acts along the length of the cylinder. So, in any given element, we had only 2 normal stresses, whereas in case of thick cylinder theory, we have 3 stresses, all the 3 normal stresses coming into picture. They are the circumferential stress, the longitudinal stress, and even the radial stress coming into picture, right. And we already talked about the distribution of the circumferential stress, right. Here we try to take the variation, and it is important to note that the circumferential stress varies and it is maximum, okay, at the inner surface and minimum at the outer surface, which you are going to see when we try to derive an expression to calculate the circumferential stress, right. So, radial stress also we have seen, okay, in this particular case, right, where radial stress is almost 0. okay, in case of thin cylinder theory, whereas in case of thick cylinder theory, the radial stress varies with the pressures that we have, okay, with respect to the wall of the cylinder. So, the internal radial pressure is physically equal to the internal pressure, and the exterior radial stress is equal to the outer pressure. And coming to the last one, the stress, longitudinal stress, in both the cases the longitudinal stresses are constant or uniform, is what you need to understand. Okay. So, let us try to move on to the thick cylinder theory, okay, more details. Now, this problem, okay, that is of thick cylinder, was first attempted by a French elastician, that is Gabriel Lamé, in 1833. Right. His objective was to determine, okay, expressions, okay, which can calculate, which can give you, okay, values for the circumferential stress and the radial stress in the wall of a cylinder at any point. Okay, and these expressions are generally referred to as Lamé's equations. Okay, and the most important problem, that part of the problem is, okay, this is an axisymmetric problem. Okay, in the sense that okay, the cylinder and the pressures, okay, they are symmetric with respect to the axis of the cylinder, and hence, okay, the sigma c, that is circumferential stress, and radial stress is not going to vary with respect to theta. So, whatever may be theta, right, 0 to 360 degrees at a particular distance, okay, the values will remain the same, but the only thing is they vary with the radial distance. So, that is the important thing that you need to understand. So, it could be at any angle, okay, it is the same, but okay, but if we are just trying to talk about the radial distances, it is going to vary. So, this is what we are trying to talk about. Now, some of the assumptions, okay, that we are trying to look at in case of your thick cylinder theory are: the first one is about the material, so which is assumed to be homogeneous, isotropic and elastic. So, we are just trying to take some metal sheets, and hence you can assume that all these properties, okay, right, characteristics, okay, are valid for such kind of materials. Okay, the stresses are within the proportionality limit. So, that means we are just in the linear part of the stress strain diagram. Okay, we are not in the non-linear stage. Okay, and the longitudinal strain remains constant for all the fibers. Please understand, okay, imagine that the thick cylinder is made of number of fibers, okay, independent, okay, individual fibers. So, the amount of strain each and every fiber along the length experiences is the same, and hence even the stresses will also be the same in each and every longitudinal fiber. So, this assumption we are going to just try to pick up, okay, and then do that in the derivation. Coming to the last assumption that we are trying to have here, the circumferential stress or the hoop stress is considered to vary across the wall thickness. Please understand, in case of thin cylinders, we had said that it is not going to vary over the wall thickness, the circumferential stress is almost uniform, whereas here it is going to vary, and it will be maximum at the inner surface and minimum at the outer surface. So, these are the 4 assumptions that we are trying to talk about in case of thick cylinder theory. My next objective is to obtain expressions, okay, for circumferential stress and radial stress in the wall of a thick cylinder. Okay, so, let us try to understand, okay, how we do this particular bookwork. The bookwork is very, very important, okay, and maybe it is quite important also. So, this is also called as the Lamé's equations, right. So, please understand, okay. So, we are trying to derive 2 expressions. So, in the beginning we did mention that, okay, the thick cylinder is subjected to a triaxial state of stress, okay, but please understand that we are more interested to calculate the circumferential stress and radial stress, okay, in the thick cylinders. Okay. So, coming to calculation of sigma L is a very simple matter. So, but however, okay, this is more important, okay, than that of your longitudinal stress. So, let us try to take a simple case here. So, we have a thick cylinder. Now, notice that the wall of the cylinder is relatively large when compared to the walls that we were trying to refer in case of your thin cylinders. So, this particular cylinder is subjected to, okay, an internal pressure Pi. So, you can clearly see that animated thing that is inside, okay, it is subjected to an internal pressure Pi, and it is also subjected to an external pressure P naught. So, sometimes that P naught may be 0, right, that means there can be no external pressure also, right, but however, the cylinders are subjected to internal pressure. So, we are trying to take a very general case where we are trying, a cylinder is being subjected to both internal pressure as well as the external pressure. So, the internal pressure in this particular case happens to be Pi, P suffix I, okay, and the external pressure is P suffix O. Okay. Now, coming to the next one, the radius, right. So, if you just try to watch here. So, A. So, A refers to the internal radius, okay, right, and B refers to the outer radius. So, you can understand that we have got two circles over there, right. So, the radius of the inner part, okay, inner surface is A, and the radius of the external surface is B. So, that is what we are trying to talk about in this particular case, right. So, let us try to take, okay, a thin shell. So, we first understand that this particular cylinder is made up of a number of thin shells, okay, of thickness dr, as you can clearly see that. Okay. So, you are trying to have dr over here. So, you can clearly see that the thickness, we are trying to take one thin shell, right, one thin shell at a radial distance r. So, that means this radius is going to vary, okay, from, okay, small a, okay, in internal diameter to small b, right, small b external diameter, and we are trying to take a small thin shell of thickness dr, right. Okay. So, this is important that we are trying to talk about. Okay. Next thing is, okay, if you just try to look at this particular figure here. Now, in this thin shell, right, in this thin shell. So, let us try to take, okay, a small element, right. So, if you can clearly see that animated view over here. So, we are just trying to pick a small element over there, and we are trying to zoom it up, right. So, please understand that whatever this thin shell that we picked up, that we are trying to have here, okay, over here, is got from that thin shell, right, one thin shell we have taken. We are trying to take one thin shell, and in that thin shell we are trying to take a small element. So, it is important to note that the stresses that we are trying to talk about, okay, in the plane, stresses in the plane. So, what are the stresses that we are trying to see in the plane over there? Okay. The stresses you are trying to look at in the plane here are, okay, at the inner surface, okay, you got sigma r, that is the radial stress, okay, that is sigma r. I hope you are trying to see this. Okay. Next, on the outer surface of this particular element, we have sigma r plus d times sigma r. There is a small change. Why? Because you can understand that in the radial direction, the pressure varies from, okay, that is pi, that is at the internal surface, to p naught at the outer surface. The stress in the radial direction varies from pi to p naught. So, we are just trying to show you that, okay, so we have, okay, a stress sigma r, radial stress sigma r, okay, on the inner side of this element, and on the outer side there is a small change, there is sigma r plus d times sigma r, and these are the circumferential stress, that is sigma c, that is on either side of the element, okay, which is nothing but the circumferential stress in that thin wall is what you need to understand over here. So, once you have here, the next thing that we are trying to talk about is we are trying to pick that, look at that closely, okay, we are just trying to pick up that, okay, that is the thin shell over there, trying to pick up that thin shell. So, you can clearly see how we are trying to pick up that thin shell, right, at a distance of r. So, we just try to take that, okay, and then you can clearly see that is the thin shell that we have isolated, okay, from the thick cylinder. And on this thin shell, right, okay, we are just trying to put the stress conditions. Now, this is important. If we just try to check, okay, the stresses that we defined on that element, we said on the interior of the element inside, the stress condition is sigma r. On the exterior, we have got sigma r plus d times sigma r. So, you can clearly see these animated arrows that we are trying to see here, that is on the inside, which represents the radial stress. So, what we are trying to talk about is all these radial stresses are having intensities of sigma r. Now, coming to the exterior surface, right here, the exterior surface, all these are subjected to a radial stress of sigma r plus d times sigma r. So, the cylinder is subjected to two different types of radial stress, that is values of radial stress, internal and external, right, and the thickness of the shell is dr. Now, at this cut surface, even the radial stress, the circumferential stresses are exposed. So, you can clearly see that, okay, at these two cut surfaces, right, you are also seeing the circumferential stress sigma c, okay, and sigma c. Right. So, you have to carefully remember and write this particular free body diagram, right. So, once you write the free body diagram, now we apply the equilibrium equation, right, for this particular diagram. So, that means we are just trying to take the summation of the forces in the y direction or vertical direction as 0 with some sign convention. So, what we are trying to talk about is, and it is very important to note that in this particular case, the radial stress is assumed as tensile, okay, right, and even in the slide, previous slide, you just saw that, okay, it is tensile. So whether it's compressive stress or radial stress, we are trying to assume the directions as tensile, right. If you get a negative sign for radial stress, it means, okay, it is compressive. So that's important, you need to understand. So you have to be careful. So when you just try to look at this diagram, we have represented both compressive stress and radial stress as tensile, right. So how do we calculate, how do we apply the equilibrium equation? It's quite simple, right. So I think if you just try to recollect the bursting force we defined, okay, in presentation 1. So the bursting force due to any pressure, okay, that is acting in the radial direction, is calculated as the product of the pressure into the projected area of the curved surface on a horizontal plane. So here we have got two pressures acting on the curved surface. The first one is sigma r plus d sigma r is what we have here. So please understand. So we try to take the intensity of the pressure. So as you can clearly see, that's the intensity of the pressure. You are trying to multiply by the projected area. So when I say projected area, it's the distance from the outer edge from here to here, right. So that would be what? So you got dr plus 2 times r plus dr, okay, which would be 2 times r plus dr, okay. The horizontal, the entire outer width is what we are trying to talk about, into 1 unit length is what you need to understand, right. Similarly, we repeat this for the internal pressure. If we just try to check the internal pressure, it is in opposite direction, and hence we have got this as minus sign in this particular case. So we just try to look at this, we have got minus. After you get minus, so we have the same thing, that is the intensity of pressure multiplied by the projection of the curved surface on a horizontal plane. So the projection of the interior surface is just 2r, that is the curved surface is only 2r, okay, into 1 is what we have here. So we have just finished, okay, two terms here. One is sigma r plus dr, the other one is sigma r. Now we are left with this particular term, that is we have here the circumferential stress. See, sigma c is on this wall as well on the other wall, that is a cut surface. How do we calculate the stress? How do we calculate the force? It's nothing but stress into area. So area is the width is dr into 1. So we got sigma c into dr into 1, and there are two values, two terms, one on this and one on this. So we get this expression as, okay, 2 times, okay, sigma c into dr into 1. So that's how we have got this particular equilibrium equations. So I'm just rewriting that particular equilibrium equation, and we are just trying to simplify this. So during the process of simplification, the first step is the number 2, that is numerical value of 2 will cancel out, and again I just try to expand, and during the process of expansion, so I get a term which is nothing but d sigma r into dr. So I hope you know that when you just try to multiply two small quantities, it becomes much smaller. Correct. So with that assumption, that is, I am just trying to ignore that particular term here, that is dr, d sigma into dr, and then I try to simplify, you get this particular equation. So I am going to just try to further simplify this equation, right. Okay, it's just a simple calculations we are just trying to refer here, and we try to rearrange, and then you get this important equation that we would be holding it, right. So the equation that we are going to get is r into d sigma r by dr plus sigma r minus sigma c equal to 0. So that's one important equation, okay, that we are trying to have here, right. So we just try to keep it, okay, and then we will come back to that particular equation later. Now coming to the wall of the cylinder. So again, this is a thick walled cylinder that we are trying to refer here. So you're just trying to see the triaxial state of stress. So you got the circumferential stress, okay, acting in this direction, correct. You got the longitudinal strain, longitudinal stress, and the radial stress. So all stresses are acting, and in our assumption we did make that the longitudinal strain is constant, is what we said. So hence let's try to calculate the longitudinal strain in this particular case. How do we calculate the longitudinal strain? There is strain, okay, in this particular direction, along this particular direction. So you can understand strain along sigma L, right, is due to sigma L, is due to sigma c, and due to sigma r. So that means we have contributions, okay, of strains, okay, in the longitudinal direction due to sigma L stress, due to sigma c stress, and sigma r stress. So you can understand the contribution of strain, okay, that is in longitudinal direction due to longitudinal stress is axial, However, the contribution of strain along the longitudinal direction due to the other two normal stresses, that is the circumferential stress and radial stress, are lateral, and hence we have this particular expression, okay, written over here. So, that is sigma L is equal to, there is epsilon L equal to sigma L by E minus nu times, okay, sigma C by E minus nu times sigma R by E, and if you just try to simplify this, so we get this as 1 by E into sigma L minus nu times sigma C plus sigma R. So, we are just trying to club these two and write here, and then we have taken, okay, E outside, okay, that is how we have simplified this. So, I am just rewriting that particular expression again. So, this longitudinal strain equal to 1 by E Young's modulus into the longitudinal stress minus nu times the summation of circumferential and radial stress. Now, it is important to note that we have stated that the longitudinal strain epsilon L, okay, is a constant. We have said that. So, if the strain epsilon L is constant, please understand the stress epsilon L is also constant, is what you need to understand. Okay. The next one is the material properties E and mu are also constant. So, what we are trying to say is this is constant, this is constant, this is constant, and that is constant. If these four parameters are constant, so what we are trying to suggest is the summation of these two stresses should be a constant, is what we are trying to say. So, that means the summation of sigma C plus sigma R is a constant, and here this constant is written as 2 times A, is what we are trying to say at this point. Okay, that is 2 times A. That is how we have written the constant. Okay. So, we now bring this equation 1. Okay. So, we just try to check, okay, equation 1. So, we have written as, okay, R into d sigma R by dr plus 2 times sigma R equal to 2 times A, right. So, we are just trying to bring that equation back here, right, and then we now try to rearrange this further. So, R into d sigma R, that is I am just trying to push this 2 times sigma R to the right and then trying to simplify that particular equation. Okay. And now, I am trying to separate the variables, right. So, that means I am going to rewrite that particular expression as d sigma R by A times A minus sigma R equal to 2 times dr by R. So, the next thing is I am just trying to integrate this particular expression. So, that would be minus log of A minus sigma R equal to 2 times log R plus C, where C is a constant. So, these are some very simple calculations that you can easily understand. So, I am rewriting that expression again. So, the last expression in the previous slide. Okay. So, what I am trying to do is I am just trying to take all log terms to the left hand side. So, you have a case where we have log A plus log B. So, which you can write as log A into B, that is A log of A minus sigma R into R square equal to minus C. And on the right hand side, as we have said, C is a constant. I am going to rewrite it as one more constant. So, that is minus C is written as, okay, one more constant in terms of log B, as you can clearly see here, there is one more constant log B. So, we just try to compare the LHS and RHS of this particular equation, equation number 3. So, we can easily say that there is A minus sigma R into R square equal to B. That means, I am just trying to say that, okay, so this term, okay, log of this equal to log of B. So, that means A minus sigma R into R square equal to B is what we are trying to say, and we can rearrange this to get the first important expression, that is the radial stress sigma R equal to A minus B by R square. So, that is the same expression which I have repeated, that is sigma R equal to A minus B by R square. Okay. So, this is an important equation. And if you just try to check in equation 2, we have said that the summation of the two stresses, that is the circumferential stress and radial stress, is always a constant, which we have written as 2A. So, what I do is I replace, okay, with equation 4 in this particular equation, that is sigma C plus sigma R. So, sigma R is replaced by RHS of equation 4, that is A minus B by R square, which is equal to 2A. Now, I just try to simplify this, I get the second important equation, that is something but sigma C equal to A plus B by R square. So, the equations 4 and 5 are what we want, okay, in this particular example, right, that is in this particular problem. The first one refers to the radial stress, the second one refers to the circumferential stress, right. So, sigma R is written as A minus B by R square and sigma C is A plus B by R square, and these equations are called as Lamè's equations. right. So, please understand, right. So, the most important equations, okay, are these two equations, that is the equation for circumferential stress and the equation for radial stress, written in a very identical way, okay. The only change that we have here is the sign. For circumferential you have a positive sign, for radial stress you got a negative sign. So, let us try to look at these expressions more carefully. So, as I did mention, they are called the Lamè's equations. So, the first one is for the radial stress and the second one is for the circumferential stress. That is, now in this particular case, it is important to note that, okay, A and B are constants, right. So, we just try to look at carefully the right hand side. So, I have written A and B, and if you just try to recollect in our derivation, we have mentioned that A and B are constants, right. So, you need to understand these constants depend on the example that we are trying to consider, right. So, that means examples, okay, whatever example we try to take, okay, the values or the boundary conditions will be different, okay, and hence the values of A and B depend on that numerical example, right. So, it is not the same. That means problem to problem, okay, the values will be different, and normally we try to calculate these constants using the known boundary conditions. So, let us try to understand what the boundary conditions are when we start some examples, okay, numerical examples with respect to this. Now, the next important thing that you need to understand here is R, right. So, we have said that in these two equations A and B are constants. So, we will just try to apply the boundary conditions, get numbers for that, and then put in these equations. Having substituted some values for A and B, and if you just try to look at these two equations, so understand the only variable on the right hand side here is R. What is R? R is the radial distance, right, correct. So, distance to any point on which in the wall of the cylinder where we are trying to calculate the stress, and obviously the radial distance is going to vary from A, small a, which happens to be the radius of the internal surface, to B, small b, which is nothing but radius to the outer surface. So, R is always going to vary from A to B, and here in this particular case, as R changes, correct, both sigma R, that is your radial stress, and sigma C are going to change, right. And it is important to note that the change is in terms of R square, right. Okay. So, when you say R square, so you can understand that the variation is not linear, it is non-linear. Okay. We are going to just try to show you how we represent, okay, the variation. Okay. It is not in a straight line, okay, it is non-linear is what you need to understand, right. Okay. Now, another important thing, if you just try to look at these two expressions. So, as I said, for sigma C you got a plus sign, and for sigma R you got a minus sign. So, that clearly suggests that the circumferential stress is always larger than the radial stress in the wall of a cylinder. Okay. And the next thing that we need to understand is, okay, how does sigma C vary, right. So, please understand you have got what is called as, right, R square in the denominator. So, if R increases, sigma C is going to reduce, or if R is less, sigma C is going to be high. And as you understand, R is going to vary from internal radius to external radius, right. So, R is minimum at internal radius. So, that means when you put a smaller value there, okay, the value of sigma C increases. So, that suggests that, okay, the value of circumferential stress is maximum, okay, at the internal surface, okay, and the value of sigma C is minimum at the outer surface. And for example, while doing numerical problems, we would be trying to give you some allowable stress, some maybe data would be given, like the allowable stress in the wall of a cylinder is something like about 40 megapascals, something like that, okay, or 50 megapascals or 100 megapascals. So, whenever such kind of data is given, so we have understood that in the wall of a cylinder always the circumferential stress are more than the radial stress, and further the circumferential stress is maximum at the inner surface, okay, when compared to the outer surface. So, that allowable stress should be always equated to the circumferential stress at the internal radius. So, that is the important thing that you need to understand. Now, we are all set to start some examples. Okay. In this particular case, okay, we are just trying to take about 3 examples here, right, 3 examples here, and we are just trying to make you understand as to how we do these examples, right. So, as you are trying to see on the screen, so you have a thick cylindrical pipe of external diameter 300 mm and thickness 50 millimeter, right. So, what is given is the external diameter and the thickness is what has been given, right. So, if the external diameter is 300 mm, so you can easily understand that the external radius is half of that, which is 150 millimeters, and since the thickness has been given, so if we deduct thickness from the external diameter, you get the internal radius, and the internal radius in this particular case is 100 mm. As you can clearly see on the screen, so the pipe, for this particular pipe, okay, small a, that is the internal radius is 100 mm and the outer radius is, okay, 150 millimeters, and this is subjected to pressures. It is subject to an internal pressure of 40 megapascals, that is Pi is 40 megapascals internal, as you are seeing on the slide, okay, and the outer pressure is 2.5 megapascals, right. So, internal pressures are generally large and external pressures are small. Okay, in this particular case, we also have an external pressure. I think the next two problems, okay, we don't have external pressures, right. Okay. So, what we are trying to do is we are trying to find out how the radial stress is going to change and how the circumferential stress is going to vary over the wall of a cylinder. So, let us try to have a look at how we do the problem. Now, the very first thing that we need to understand is, okay, we write Lamè's equations. I hope all of you know, okay, how we write the Lamè's equations. So, there are two equations that we are trying to write here. The first one is for the radial stress, that is sigma r equal to a minus b by r square. The next Lamè's equation that we write here is the circumferential stress sigma c, which is equal to a plus b by r square. So, here a and b are constants, as you understand, and we have to evaluate. So, whatever values that we are trying to calculate right now is specific to this data. Okay. So, let us try to see how we calculate the values of the constants a and b for this given data. So, as I said, we are talking about some boundary conditions. Now, the boundary conditions that we have here is given internal pressure is 40 megapascals. That means, the pipe is subjected to an internal pressure of 40 megapascals. So, when you say internal pressure, where does it act? It acts along the internal surface. So, what is the radius? The radius is, okay, 100 millimeter, and internal pressure acts in which direction? Radial direction, correct. So, what you need to understand is this statement, given internal pressure of 40 megapascals, should be understood as, okay, the value of sigma r, right, is 40 megapascals, and the distance, okay, at which distance, at what value of r we are having this 40 megapascals, it is at the internal surface, which is 100 millimeter. And the most important thing that you need to understand here is you have to have a minus sign for this, because if you recollect that free body diagram that we wrote, we also considered radial stress to be tensile. Okay, but understand, when you just try to take the wall and then subject it to an internal radial pressure like this, correct. So, if you just try to take the element, okay, the element on the inter boundary, it is subjected to compression, right. So, we are going to write it as minus 40 megapascals. Right. Now, this information we have to put in which equation? Is it equation 1 or equation 2? Equation 1 is for radial stress, equation 2 is for circumferential stress. So, we put this in the equation 1, that is for radial stress, and we write this equation, that is minus 40 equal to a minus b by 100 square. So, I have just taken equation 1, replaced sigma r with minus 40, replaced r with 100 is what I have done here. So, I have got equation number 3. Right. Now, let us try to go to the second boundary condition that we have here. The external pressure is 2.5 megapascals. So, when you say external pressure, it is also a radial pressure. It is also a radial pressure, that is, we try to substitute it as minus 2.5 megapascals, and it is acting at this radial distance of 150 mm. Right. And again, important, minus. Okay. This is also compression, right, surface subject to external pressure. Okay. So, we have to be very careful. Minus 2.5 megapascals. So, again, this is radial, I put in equation 1. If I put in equation 1, I got an equation minus 2.5 equal to a minus b by 150 square. So, I got two equations, two unknowns. I solve and get the values of a and b. So, the value of a and b you are trying to see on the screen, 27.5, and b a very large number, 675 followed by 3 zeros. Now, these concepts are problem specific. So, I now substitute these values in equations 1 and 2, and you have an equation ready to be used, that is an expression for sigma r, an expression for sigma c, correct. Now, what is it I am trying to do from this? So, I can just go on varying r, okay, in both these expressions and try to calculate the values of sigma r and sigma c. right. So, normally what I do is I try to take this equation number 5 here, okay, substitute the values of r, okay, one at A, one at B, internal, external. I get the values at the intersurface, internal and external surface. Similarly, I try to take equation number 6, substitute r, okay, once with the internal radius, once with the external radius, and get these numbers. And that is what I have done here. That is, if I just want the hoop stress, okay, I substitute numbers here and then try to get, okay, what is the hoop stress at the internal radius, what is the hoop stress at the external radius, correct. And here I am trying to get positive signs, which means it is tension. Similarly, I just try to take the other expression for radial stress, substitute the values of these radius, okay, internal and external, and I get numbers. And you need to be very clever here. It is really not necessary for you to substitute these numbers, because already you know this information. Even if substitute, you get the same thing, right, but it is not nice to substitute and waste time, right. You can easily understand by common sense that the radial stress at the interior has to be minus 40 megapascals and the outer surface is 2.5 megapascals. So, with this we can quickly draw the stress distributions, okay, with respect to the walls of the cylinder. So, what I am trying to show you here is, okay, one half of the cylinder, right, radius, internal radius 100, external radius is 150. So, on the left hand side of a screen, I am just trying to show you how the circumferential stress is going to vary. The circumferential stress varies from 95 megapascals at the internal surface to 57.5 megapascals at the outer surface. Please understand, there is a good difference, huge difference between these values, and the most important thing is how is it varying. It is not varying linearly, it is varying in a non-linear way. It is not linear, non-linear, r square, please understand. Similarly, on the RHS of your the screen, you are trying to see the distribution of the radial stress. So, it varies from minus 40 megapascals to minus 2.5 megapascals, okay, that is compression. I have written in below that compression, right. So, minus 40 megapascals to minus 2.5 megapascals, okay, they are nothing but Pi and P naught. So, this is how you need to understand, and both the distributions are radial. I hope you have understood, okay, the concept of this problem 1. So, the next two problems run on similar lines, right. So, some given data in this particular case are the internal radius 120 millimeter, okay, external radius 150. So, you can calculate the thickness, okay, the internal pressure is given as 40 megapascals, that is it. Please understand, nothing has been mentioned with respect to outer pressure, and we are assuming it to be 0, right, because nothing has been given. So, we try to take P naught to be 0. So, this is important, you need to take this value. So, again we try to write these two equations, Lamy's equations. We want to calculate the constants A and B. We apply the boundary conditions. What are the boundary conditions? Okay, we know the internal pressure is 12 megapascals. So, where that is at r equal to 120, substitute the value of sigma as minus 12 megapascals, put it in equation 1, okay, you get, okay, the value of you get the first equation over there. Similarly, we apply the second boundary condition, and the second boundary condition is assumed in this particular case. The cylinder is not subject to any external pressure, is an assumption that we have made. No data has been given. So, with that understanding, we try to give you the data as r equal to at that is outer radius 160 millimeters, okay, the radial stress is 0. So, we try to put back again in equation 1, we get one more equation, right. So, and now we try to solve, get the values of A and B. So, once you get the values of A and B, we try to put back these constants in the equation, and you have got that equations for radial stress and circumferential stress. So, with this equation, right, you can understand the constants are quite different from what we have got. So, with these constants, it is possible to calculate how sigma r is going to vary with respect to the wall of the thickness, how sigma c is going to vary with respect to the wall of the thickness. So, similar to what we did in the previous problem, we have just tried to calculate the circumferential stress at the inner surface, the circumferential stress at the outer surface, right, the radial stress at the inner surface, which is nothing but Pi, and the radial stress at the external surface, which is nothing but 0. Now, one more information we are trying to calculate in this particular exercise. What if you calculate the circumferential stress with the expression of thin cylinders? So, this is the expression, this is the value that actual value we got, okay, from Lamy's equations. That is, at the internal pressure at the internal surface, sigma c is 42.86 megapascals. But if you try to calculate the thin cylinder theory, circumferential stress by thin cylinder theory, it is PD by 2T, which happens to be 36 megapascals. The correct value is 42.86. But the approximate value from thin cylinder theory is 36. There is huge difference, and you can always calculate the percentage error, that is the difference divided by the actual value, which happens to be 16% in this case. Now, coming to the last example, right, an interesting example. So, here in this particular case the internal diameter has been given as 200, we have an internal radius of 100 mm. So, you can convert it. The internal pressure has been given to be 40 megapascals, right, and the allowable stress has been given in this case for the material, which is 120 megapascals. External pressure has not been given, so we just try to take it as 0, and now in this particular problem we want to calculate what is the thickness T, okay, of the cylinder, right. So, again we go back to Laplace equations, two equations, right. We have two constants, we have to evaluate. So, using the boundary condition. So, boundary conditions, let us try to understand. So, the internal pressure is 40 megapascals, right. So, you substituted as R equal to at 100 mm, the value sigma R equal to minus 40 megapascals, put in equation 1, you have one equation available. Now, we have got one more boundary condition, the allowable stress in this particular case. In the two problems, previous problem, we knew the thickness. So, we use the boundary condition as at the outer surface the radial stress is 0, whereas in this particular case the allowable stress is given as 120 megapascals. As you understand, of the two stresses sigma C and sigma R, sigma C is always larger than sigma R, and further sigma C is maximum at the inter surface. So, we now use the condition at R equal to 100 mm inter surface, right. So, this circumferential stress is plus, it is not minus, plus 120 megapascals. So, we substitute this in equation 2, not 1, right, and we get one more equation here. Solve, get the values of A and B. Once you get the values of A and B, put back, okay, in equations 1 and 2, equations are ready, right. So, that is how we try to do this particular problem. Once the equation is ready, now we try to apply boundary condition number 3 to calculate the thickness. And what is boundary condition number 3? External pressure is 0, right. So, we are going to say at R equal to 100 plus T. So, what is 100? The internal radius plus thickness, that will give you the external radius. So, the external radius is calculated as small a plus T, small a is 100, okay, the value of sigma R equal to 0. Now, I try to substitute back in equation number 5 which you are seeing on the screen. I put this in equation number 5 and you get that, the only unknown being T, and you get the value of T, right. The value of T in this particular case is 141.42 millimeters. Well, students, I hope you have understood these examples, right. So, I think in overall if you just try to look at this, so we have discussed two theories here, thin cylinder theory and thick cylinder theory. So, I hope with this three presentations on thin and thick cylinders and with my notes which I have passed on. So, I hope you should be able to clearly understand and do any kind of numerical examples. Thank you.